that okay? Okay. Good morning, everybody. Yes. We are here to continue from where we stopped yesterday. Now, I gave you a work to do. One-dimensional wave equation. Did we try it? I gave you something like this. Now, this is actually one-dimensional heat equation. For some of us who might begin from mathematics, you may decide to look at the solutions. The way it is done, you can look at the Stevenson, and then you see the solution to be what we have. Please, next slide. Okay, now you will see equation 2.5 actually gives us its solution. But you ask me how. You see, if we look at that problem 2.4 and then assume that the solution looks like that we have two solutions. One is this to be equal to x minus ct, and the other one will be theta equal to x plus ct. That is our 2.5. You see, the substitution of this equation 1 and 2 into this will give you equation 2.6. Can we try that? It's an ability to check how you can use your partial differentiation. All right? First of all, we'll try to build in. You see, partial 2u by partial t squared. There's a t squared here. Now, and then you are using this, which contains t, and at the same time, x. Theta also. So we need to put that into consideration. One, we need to find out what is partial by partial t that will contain these two new variables we are introducing. So what do? You will see that might give you partial by partial this by partial t. We have taken care of that. Now, because there are two, you should go to also do the same. Partial by theta by t. And when you do that, when you differentiate this with respect to t and that, then for this by this will give you what? Partial by partial t of all that you will have there. You know, when we differentiate this with respect to t, we'll have a minus c, is it not? To shorten it, you're going to have a minus c of what? Partial by partial this plus c partial by partial theta. Now, you will see we have something like this. The next thing you will do is also to write this in terms of this and this, which means if I take out a c because it's common, I'm going to have partial, as I have done, by this by t plus partial of theta by t. This will operate on this particular one. You see that? Then the same thing goes on. That gives me, I'm going to have a c squared somewhere. Okay? Because this will give you minus c and this. So I'm going to have c squared of minus of this plus this will operate on the same. You can multiply that out. This on this gives you a positive number. This gives you, so you're going to have, just like when you have a minus b all squared. Okay? That gives you a squared minus 2ab plus what? B squared. So we're going to have that as c squared into, I will have partial 2 by partial this squared plus partial 2 by partial neta squared minus 2 partial 2 by partial neta partial this. That is exactly what I will get. So, because of the substitution we are making, the left-hand side takes this to operate on u. All right? So, we're going to have c squared. You'll have your partial 2u by partial t squared is equivalent to c squared into partial 2 by this plus partial 2 partial neta squared minus 2 of this of neta of this operating on u. Any problem so far? Huh? We can do the same thing for the x. And in that situation, you should also build from what I'm cleaning here, because this is, I think that's our first semester, year 2, undergraduate. Yes. Yeah. Okay. Now, you can also do that. Partial u, partial by partial x. You follow the same. You see, when we differentiate this, you're going to have partial by partial this by partial x plus this of neta by x. This one looks a little bit simple because we are not going to have a c. There you will pick 1 because the differentiation of this will give you 1. The other one with respect to x will also give you 1. So that's actually gives us partial by partial this plus partial by partial neta. And then if you take the second one, you're going to have partial 2 by partial this plus partial 2 by neta squared plus 2 partial 2 by partial neta by partial zeta. So that's exactly what we'll have for x. You combine the two of them together. So when you combine the left-hand side to the right-hand side, you are going to pick up c squared into partial 2 by partial this squared plus partial 2 by partial neta squared minus 2 partial 2 by partial neta partial this. Now note that partial 2 by partial neta partial zeta is the same as partial 2 of the zeta of what? This. So we can, because you're operating the other way around. Yes. So that's equal to c squared into partial 2, well, operating on u, of partial this squared plus partial 2 by partial neta squared plus 2 partial zeta partial neta operating on u. Now you will see c squared will cancel c squared. This and this will cancel each other. You'll be left with what? Minus 2 partial 2u by partial neta partial z equal to 2 of partial 2u partial this by partial neta, which actually gives you 4 of partial 2u by partial neta partial zeta equal to 0, which of course gives you equation 2.6. Okay? So you see, it's a long way you have to do so that we can achieve success. And of course, with two differentiation, well, we need to integrate to get our results. When you integrate the first time with respect to neither, it will give you a constant. You differentiate the other one, integrate the other one, it will give you. So you will see, they carefully told us, which we will experience from the solution of this, that our u, you can go to the next slide, I think so. You will see that your u will not be a function of this and neta. And then in that case, it will give you what we have as r this plus r neta. So what are those solutions? Those solutions, you have that. Where's the pointer? Have I thrown it? Okay. Now you see, that is what this is, and that is what this. The next slide. The next. Huh? Okay. No. Okay. So, let me go down. Why? No, I need to write the solution in terms of u, x, and t, which will actually, which one are you using? Are you using the PDF? Is that one cut off too? Okay. So that you will have r, which will give you x minus ct plus L. Well, we could look at this as you have x plus ct. So these are the two solutions that we are trying to get there. You see, r and L are arbitrary functions, and they are traveling with what? Velocities. The velocities they are traveling with, you can say one is a plus c and one is a minus c. That is what we can get. But for us to now look at eigenmodes, we'll be able to appreciate the solutions more when we go to the eigenmodes. All right? In that case, we will assume that the solution is somewhat. Please. Okay. Now, for the eigenmode solutions, we will assume that u, a function of x and t, will be equal to a function of x multiplied by the exponential of minus this, which is a function of t. All right? So all you do is to substitute that into this equation. Can we do that so that we don't take enough time? Differentiate the first one with respect to x and differentiate the second time. You put the value, you will have d2 by the x squared, whereas the exponential gives you omega squared, which we now divide to show you that k is equal to omega over what? C. That gives you that equation. You can see that equation is very simple to solve. It's a wave equation. And then you want to solve that, you can easily make a substitution. Is it not? How many of us have forgotten? Because this is the foundation of what we are going to be seeing. We will need to do this as we go on to solve these our wave problems. We have something like this: d2 by the x squared plus k squared of f equal to 0. It's quite easy to solve, is it not? You can say that your f is equal to what? EMX to be your solution, so that your d2 by the x squared of f gives you m squared. So you have m squared plus k squared is equal to 0. M equal to what? Plus or minus ik. So that is exactly how you will see that your f of x of t or f of x will give you what? That solution. You have a constant times that. And then when you do that in terms of a trigonometrical functions, it's going to give you a cos that. We have introduced that to be our phase. All right? If, depending on the boundary conditions you give, you may decide to, you may have a solution that eventually will give you, which is now dependent on the, on what? Frequency. Because we are looking at that. Frequency must be there whenever we are talking about wave. So it could either give you a cos of k x plus omega t, or it could give you a1 sine of k of x plus omega t. These are functions. You can plot them and you will see they generate wave of this form, where you can now begin to talk about the situation. So that's exactly how the first one-dimensional wave equation looks like. You can plot them. Maybe at the end of the class, our director will help us with Mathpool. But I can also help you with Mathematica, so that you can see the picture of whatever you are solving. You have to see it. Then you'll be able to see what will be the amplitude of this vector, of this wave. What will be the frequency? What will be that? What will be that? Then you'll be able now to explain about the physical environment that is generated by such a wave. All right? Okay. Now, I tried to get a problem which is not part of my notes, so that we can also appreciate how this is done. It follows almost the same thing, but we want to look at it to give it some kind of applications that might come from the solar atmosphere. Can you do that now or later? Okay. So you can follow me and we'll write. This is not part of your note. I have to do this extra in the night to see that we understand. Please, in case you have any problem, any question, let us know. Yes. Yes. 2.11. What happens there? Uh-huh. Uh-huh, now what happened? No. You see, this is a standing wave. What we try to look at is, if you go back, you will see where we talk about the parameters of a wave. Huh? Did we? Okay, let's see. Where we talk about, see the parameter. We must represent our wave for the study. You can see that equation. Are you seeing it? That is why when you have the wave equation of that form, we will try to reduce it in what? In a frequency domain. What we do in a stability theory, we call it normal mode analysis. Normal mode analysis. Because in the normal mode analysis, the frequency or the Fourier you are taking tells you that it must be, the temporal must be what? Exponentially informed. And then being raised to power of imaginary number. So with that, e raised to power of ik minus omega I will give you a dispersion relation that will be a function of the frequency. All right? Because what we are doing here also is a background or building block to instabilities. Well, I wonder, because it's going to be a long lecture, that's why we are trying to look to restrict ourselves to days without the instabilities. Maybe if there's opportunity or we can work, there are a lot of instabilities that can come in. But the principle is normal modes. We are not taking our U as a perturbed quantity, because all we are trying to do within this zone is to look at the effect, the solutions of the perturbed quantity. Because we said they are small compared to the stationary value. All right? Okay. Yes, sir.
The question is asking, if I understand it correctly, he's talking about the f. We assume f to be exponent fx. That doesn't ask it. The why he's doing that is because we look at the differential equation that is written.
This
Constant
coefficient.
So it is, I mean, we're going back to year 2 now. Where we're getting that. That is not reason to do that. If it is variable constant, it's not going to do that.
I'm not going to do that.
It is constant coefficients, and therefore we can do this. Answers. Yes. Answers. No, we don't really guess.
No, we don't.
We don't say guess.
You don't guess.
This is differential equation of constant,
Can't call coefficient.
and therefore the solution
Son.
is assumed to be that because exponential.
We just assume that.
So based on that, but if it is answers,
It's an assumption. Okay. Because you are referring me to equation 2.11, which is far from that. That's why I had to start to explain. Okay. All right. Now we take another problem. This is actually a problem that concerns with the internal wave system. And then what we call internal gravity waves. The parameters will be given to you. Then you get the solutions. And you'll be able to plot these solutions and give us an interpretation. It's not different from this. But because there are parameters, let's bring it back to the physical environment than solving the problem. Okay. let's say we have a differential equation dw of 2 and dz squared plus mu squared of w equal to 0, where your mu squared is equal to k squared of g beta s beta minus omega squared minus 1. And then we have conditions that must be satisfied in this case. It says w is equal to 0 at the boundaries, z equal to 0 and then h0. These are our boundaries. Now, we want to solve this problem. The previous problem we solved contains what the question is. But in this case, we need to now apply these conditions, okay? I may not go through the process again because we should understand that the solution of the problem will give you w as a function of z. We'll give you, say, a cos. We look at it as mu z plus b sine of mu z. Any query? It follows the same method as we did here. You see where we have written the solution. So, okay? All right. So what do? We need to... You don't need to differentiate because the boundary condition does not contain differential. All you do is to put w is 0 when z is 0. So if you do that, first you have 0 will be equal to a plus what? B. Is it not? The first condition gives you that what? A is equal to 0. And your problem now comes to this. Will be equal to b sine mu of z. Now the second tells you that h0 will give you b sine mu h0. Is it not? Are we correct? It's also 0. This will imply that mu h0 will be equal to n pi, where your n will be from 1, 2, and so on. So you can now see with this, we see that mu will be equal to n pi over h0. Is it not? Huh? So because we are looking at this, it's no longer one value because there are multiplications where you have these angles, n pi, 1 pi, 2 pi, 3 pi, and so on. That will now help you to see how it is going. Okay, so this actually implies that mu n will give you n pi over h0. And you can now write your solution to see that your mu now, which have been given, you will see that your mu n squared. All we are going to do is to get these values out and then take it in the way we want to look at it. And then you are going to see that this will actually give you k squared g beta s beta minus 1 all over mu n squared. So what are we going to look at? You do this. You are going to have k squared all over mu n squared into g beta s beta minus mu n squared. Am I correct? Uh-huh. So you see that mu n squared omega n squared will give you k squared g beta s beta minus omega n squared. I've cross multiplied. So we can bring this to be able to write the dispersion relation. So you have this coming over here will become plus. So you're going to have mu n squared plus k squared omega n squared will give you k squared g beta s beta. You can now find the value of omega n. That gives you that omega n squared should give me k squared h naught squared g beta s beta all over n pi squared plus h0 k squared. This is now our dispersion relation, which is the key entity in the development of waves. So that is, you can take the square root. You will see that your omega n will give you the square root of that. We'll have k h0 square root of g beta s beta over n pi squared plus h0 squared k squared. Now, from here, it's easy for you to have your phase speed, which will be omega n over what? K. And you differentiate that quantity, you get your group velocity. So you can see that this is not that difficult as we are going to look at it. Huh? Okay. I will give you another homework. Huh? All you will do is to try and solve these problems. And then we'll go on from there. I will leave this with him. The problem I want to give you is here, but I've solved it, but you'll try it on your own. Huh? Okay. This one you will solve it by separation of variables. Let's see, begin to know that you can do such things. Okay. This is, we'll need this one tomorrow, not the one we'll say today. You didn't do anything though. This place is hot to be cold. Huh? My colleagues and I will stay awake till 12 o'clock, 1 o'clock. So what do you do with your time? Check your WhatsApp. You know, the Laplacian. Okay? That is the Laplacian. Okay? So you try to do this by separation of variables. You have the spatial and temporal solutions. Aha. You see, my director is shaking his head because if I make mistake, he will sack me. So you will do this and give me back my paper. Okay. There are 6 pages. No, hold it now. You can find something and staple it. Wait one second. Okay.
That was the night.
You find nice.
As a little bit of this story.
No, no worry.
I wanted to call that the midnight.
No. I was awake by up to 12. Though there was no light, the generator had some problem, so I had to use my torch. Because I did. Huh? In the night. I think that was about 9 or so. The generator developed some fault. They said this morning they have called the engineer to come and work on it. It's okay. Like I said. No, it's okay. Eh?
Like the place you go before, you can't do that. There are lots of snakes and pythons inside there.
Where? That place.
Yes.
You should buy bitter cola.
Spectacular.
Buy bitter cola, throw inside there. You can also get kerosene and diesel. Put things like waterproof at the entrance. Pour that because any snake that touches kerosene is gone. There's also plants.
The place is bad. We have not been able to do anything. Anybody who bothered to go to that place is
I know. Negligence.
no, they're not ready. But we'll tell them. We'll tell them every day that that's it to listen.
Okay, we'll continue. I'm taking 5 minutes, so at least I still have 2 hours.
Before the first break.
Huh?
Before the first break.
I'll finish by 12 now. I have 2 hours to the break. So that is when let's do small thing. Network is bad, yeah. Network.